How does one study what one cannot see? Over the centuries, investigators interested in the structure of the atom have worked pretty much in the dark. Until the day that Henri Becquerel developed a piece of photographic paper on which had been placed a uranium compound. The discovery of radiation led Ernest Rutherford to devise the first tools with which to probe the atom directly. From the newly discovered element polonium, Rutherford identified emanations which were absorbed by a lead box. A hole allowed this radiation to escape, and some could be detected on a screen. A strong magnetic field bent one set of rays slightly in one direction, and another set of rays strongly in the other. This indicated that the rays consisted of particles which had both mass and charge. Rutherford dubbed them alpha and beta particles. The alpha particle, being fast, massive, and positively charged, seemed the ideal probe with which to penetrate the atomic surface. Rutherford's probe consisted of a point source of alpha particles, a sheet of gold foil, and a zinc sulfide detection screen. Rutherford found that most of the alpha particles passed through the gold foil with little or no detectable change of direction. Occasionally, however, the detection screen showed that a particle had been deflected significantly. More rarely yet, a direct rebound could be detected, an event which, as Rutherford described it, was like firing a large naval shell at a piece of tissue paper and having it bounce back and hit you. These findings indicated to Rutherford that much of the gold foil must, at the atomic level, be empty space. But what in the foil was causing a small number of the alpha particles to be scattered from their original line of motion? One possibility, the alpha particle was colliding with some other particle, in the same way that two hard billiard balls collide. This kind of collision produces a distinctive pattern. Although Rutherford could not see the individual tracks, he intercepted them with screens at many different positions until he built up an idea of the actual pattern produced. And it was quite different from our earlier pattern of billiard ball collisions. So Rutherford looked to Coulomb's law for an explanation. The force of repulsion between two particles with the same charge increases as distance decreases. Is it possible that the positively charged alpha particles were being repelled by a nucleus of positive charge within the gold foil? Let's consider what would happen to an alpha particle on a direct head-on collision course with such a positively charged nucleus. We will show only the force exerted on the alpha particle. As the alpha particle approaches the nucleus, the force acting on it rapidly grows larger, causing the alpha particle to slow down, stop, then accelerate back in the direction from which it came. Let's look at it again. about an alpha particle which is on a path which would take it just past the side of the nucleus? Consider first if no electrostatic force were acting. But if the nucleus carries a positive charge, the electrostatic force will grow rapidly as it did before. Since the alpha particle is not on a direct head-on collision course, the electrostatic force exerted by the nucleus affects not only the speed of the particle, but also its direction. Let's look at it again and stop the action completely. The force of repulsion can be broken into two components. The component parallel to the path of the alpha particle slows it down, while the other component, perpendicular to its motion, changes the direction of the particle. A characteristic curve is traced as one charged particle interacts with another. By assuming the existence of a positive charge, Rutherford was able to mathematically calculate a scattering pattern which matched those observed in his gold foil experiment. What was this mysterious positively charged particle? Well, Rutherford knew that the closer an alpha particle came to the mystery, the greater the angle at which it was repelled. So he was able to estimate the distance of closest approach. He found it to be astonishingly small. The positively charged particle at its center could have a radius no larger than 3 × 10⁻⁻14 meters. Even if the tiniest dot on this screen represents its nucleus, the atom itself is gigantic in comparison. It was Rutherford who coined the term nucleus and applied it to this tiny central core lost in the vast space of the atom. He proposed a structure for the atom which mimics, in miniature, the solar system. The tiny, heavy nucleus is orbited by lighter electrons. The force of attraction between the electron and the nucleus prevents the electron from flying off into space. But it is not great enough to cause the moving electron to spiral into the nucleus. Rutherford's model represented a significant step forward in our understanding of the atom. But in the end, it presented problems. Classical physics theory predicts that an accelerated charge will produce electromagnetic radiation, a form of energy. Well, an electron moving in a circle at a constant speed is an accelerating charge. And yet, if it continually radiates electromagnetic energy, it is obviously losing that energy. This should cause it to drop towards the nucleus, where it will rotate more frequently, thus increasing the frequency of the radiation. But this kind of increasing frequency shift is never observed. Eventually, the electron should lose so much energy it would spiral into the nucleus. But in reality, most atoms are very stable. The Rutherford model, if it was to survive, needed help urgently. The problems facing the Rutherford model of the atom had their source in the demands imposed by classical electromagnetic theory. Classical electromagnetic theory predicts that an orbiting electron should emit radiation. It predicts that this radiation will change in frequency as the electron loses energy. Eventually, the electron will spiral into the nucleus, causing who knows what to happen. But we can see with our own eyes this prediction is false. Some atoms glow in the dark by emitting visible radiation, but they do not change color, which would indicate a frequency shift, nor do they blow up, disappear, or otherwise self-destruct. It would seem that in its attempts to describe the atomic structure, classical theory delivers us to a frontier. Beyond this frontier, the laws describing some things must be radically different from those envisaged by Newton. Working under Rutherford was a brilliant young theorist, Niels Bohr, who came to the rescue of Rutherford's atomic model. He suggested that the laws governing the motion and behavior of large bodies and particles are inadequate to explain all the motions and behaviors of atoms and electrons. He proposed that an orbiting electron, despite the fact that it is an accelerating charge, does not necessarily radiate energy. A relatively new proposal put forward by Max Planck, who in the late 19th century had held the Berlin Chair of Theoretical Physics, provided Niels Bohr with his starting point. Planck proposed that matter, when emitting or absorbing radiation, does so not continuously as had been thought, but rather in discrete bundles of energy. Each bundle is called a quantum. Bohr knew that electrons traveling close to the nucleus in small orbits possess less energy than those moving in larger orbits. This is because an electron near the nucleus is attracted more strongly by the nucleus than one that is further away. Energy is required and work must be done on an electron in order to move it from a small orbit to a large orbit. Bohr reasoned that the energy difference between the smaller and larger orbits must somehow be related to Planck's discrete bundles or quanta of energy. This led Bohr to conclude that around the nucleus of an atom, an electron may occupy only certain precise orbits or energy levels. Bohr predicted that for the hydrogen atom, the radius of those allowable orbits was given by an equation directly related to the orbit number. Because the radius depends on the square of the orbit number, the distance to successive orbits increases rapidly. There is no theoretical limit to the number of orbits. Bohr developed another equation to predict the speed of an electron in each orbit. Most important, Bohr found a way of calculating the energy of the electron in each orbit. It's a function of the speed of the electron and the attraction between the nucleus and electron. which, as Coulomb's law describes, depends on the square of the distance between them. Using this formula, Bohr predicted the energy levels for each of the allowable orbits in the hydrogen atom. In formulating his concept of atomic structure, Niels Bohr concerned himself primarily with the simplest atom, hydrogen, which has one electron. By calculating the possible energy levels of orbiting electrons, Bohr was able to explain the specific frequencies of radiation that can be detected when hydrogen is under constant bombardment from moving electrons. In Bohr's concept, a free electron may eventually collide with an orbiting electron. Such a collision can transfer energy to the orbiting electron. The question is, how much energy must be carried by the free electron in order to knock an orbiting electron out of its orbit? What is needed is enough energy to overcome the difference between this orbit and another higher orbit. In this case, if the energy of the bombarding electron is less than 10.2 electron volts, there will be no interaction between the target atom and the free electron. But an electron of exactly 10.2 electron volts can give up all its energy to an orbiting electron in the ground state and bounce it up to the first excited state, n equals 2. The free electron will escape from the atom with zero energy. An electron is not limited to a jump to the nearest higher orbit. It can jump to a farther orbit, as long as a colliding free electron has at least enough energy to equal the difference between the orbits in question. In every case, any leftover energy is retained by the free electron. If a bombarding electron has and gives up more than 13.6 electron volts to a hydrogen atom, the orbiting electron is liberated from the nucleus, and the atom becomes ionized. The energy difference between orbits is the key to explaining the hydrogen spectrum, because electrons quickly return to closer orbits. Bohr proposed that the electron, in returning to a lower orbit, would give off, in the form of a photon, a quantum of energy that exactly equals the difference in energy between the two orbits. This photon is, of course, detectable radiation. For the hydrogen atom, Bohr calculated the energy differences between all the allowable orbits and the frequency of a corresponding photon. Just how well did Bohr's model predict the hydrogen spectrum? We'll find that out in the next program. The model was certainly good enough to be a passport for the atom to enter into the world of modern quantum physics. The classical model of the atom became obsolete in the early 20th century. Then Niels Bohr made a series of revolutionary proposals that allowed the model of the atom to cross into the land of quantum physics. Bohr proposed that an electron orbiting the nucleus of an atom is constrained to occupy certain definite orbits or energy levels. It does not normally emit radiation, not in the ground state or closest possible orbit, or in any excited states, as the further permissible orbits are called. Bohr explained how atoms emit radiation based on the energy level of an electron in each orbit, and used these values to predict all possible frequencies of radiation for a hydrogen atom. Bohr's predictions could be put to a practical test because detailed observations had been made of the frequencies emitted when hydrogen is bombarded with electrons in a discharge tube. In the late 19th century, a Swiss schoolteacher, Johann Balmer, had observed the spectral lines in the visible region of the spectrum of excited hydrogen gas. What's more, he had developed a formula that correctly predicted these lines. In 1908, the German physicist Paschen detected hydrogen emission lines in the infrared region of the spectrum of excited hydrogen gas. In 1914, Theodor Lyman identified the ultraviolet region of the spectrum. Bohr's predictions matched all these observations to a high degree of accuracy. Still, Balmer had already produced a workable formula for predicting lines, but no one really knew why it worked. What made Bohr's mathematics so special was that they were based on a possible structure of the atom. Imagine that a collection of hydrogen atoms could be gathered, all in the ground state. Further, imagine these atoms could be bombarded by precisely tuning the energy of every free electron in a spark tube. At the lowest energy levels, the hydrogen would emit no radiation. But at a certain level, radiation would begin. What level? According to Bohr, the level of the next possible orbit. When this magic number is reached, hydrogen would emit one and only one frequency of ultraviolet light. But why just one frequency? Free electrons would have just enough energy to bump the orbiting electrons up to the first excited state, n equals 2. This action would cause no radiation to be emitted, but eventually the electron would spontaneously drop back to the ground state. In so doing, it would radiate all the energy it had gained, the difference between the energy levels of the two orbits, exactly 10.2 electron volts. Using Planck's constant, the wavelength of this photon can be calculated exactly. This frequency is in the ultraviolet region of the spectrum. Bohr proposed that each emission line in a hydrogen spectrum corresponds to the energy difference between two specific permissible orbits. The Balmer series is produced as electrons drop between orbit n equals 3 to n equals 2. N equals 4 to n equals 2. And so on. Infrared radiation in the Paschen series is produced by jumps to n equals 3. Ultraviolet radiation in the Lyman series is produced by jumps to n equals 1. Bohr had produced the first real explanation of a frequency spectrum, every line corresponding to the energy difference between two permissible orbits of an electron about the nucleus of an atom. Bohr's model of the atom cleared up another mystery of science, which had been of great practical value, but was completely unexplained. Early in the 19th century, the English scientist William Wollaston observed 7 dark lines in the spectrum of sunlight. A decade later, Fraunhofer resolved these initial 7 lines into many hundreds. In 1860, Kirchhoff found that when an intense light source is shone through a spectrometer to produce a spectrum, and then a sodium flame is interposed, some of Fraunhofer's dark lines are produced. Kirchhoff recognized that a substance capable of emitting a certain spectral line has a very strong absorptive power for the same line. Bohr's model suggests the reason. An electron can emit a particular frequency as it drops from one orbit to another. It can also absorb a photon of exactly the same frequency, which gives it the energy to jump in the opposite direction to a higher excited state. Long before Bohr's explanation, Kirchhoff's work had produced the technique of spectral analysis, which has enabled scientists to determine the composition not only of earthly chemical compounds, but substances beyond the Earth, including the sun and the stars as well. Here's how it works. An intense light source like the sun radiates in all directions. Only a portion of all radiated light, however, is directed toward an observer. If a sodium flame is placed in the path of the light, the sodium absorbs and then re-radiates only certain frequencies. This re-radiation likewise occurs in all directions, so that only a tiny portion of the absorbed frequency continues in its original direction. The result is a sharp decrease in the intensity of the light reaching the observer from that portion of the spectrum, and hence the appearance of dark lines in the spectrum. An imaginary sunbather whose skin was sensitive only to the absorbed wavelength would take a long time to acquire a tan. Fraunhofer's many dark lines are produced as atoms in the sun's atmosphere absorb and re-radiate particular frequencies. Bohr was able to use his model of the atom to predict the results of many scientific experiments. And yet there were problems. For example, his theory worked for hydrogen, but could not predict the behavior of other atoms. Nonetheless, Niels Bohr had made tremendous strides along the road to an understanding of atomic structure. Bohr had bagged the quantum. discovered that the laws of physics which govern the motion and behavior of large bodies was not adequate to account for the motion of tiny particles, such as atoms and electrons. With his model, Bohr could explain the behavior of atoms with one electron. But he could not predict the radiation spectrum observed for other, more complex atoms. The seeds of a new model would come from the concept that all forms of electromagnetic radiation exhibit the properties of waves and particles. This concept led the aristocratic French naval officer Louis de Broglie to speculate that particles of matter might also exhibit wave characteristics, although these waves would not be obvious at the scale of day-to-day observation. Even in the bathtub, we can see two waves interact to produce a larger wave, then pass right through each other without injuring each other. Imagine two particles, like a baseball and a bat, somehow becoming one, then passing right through each other. And yet, experiments with particles as small as electrons show they produce patterns we can only explain with waves. The pattern can be produced even if only one electron at a time passes through the slits. De Broglie suggested that his matter waves would have a wavelength inversely proportional to the electron's momentum, which could be calculated by multiplying the mass of the electron by its velocity. De Broglie showed that by using his matter waves, he could predict each allowable orbit and its radius for the hydrogen atom. He also came up with the same energy levels as those predicted by the Bohr model. De Broglie proposed that in the ground state, or first energy level, the circumference of the electron orbit is one de Broglie wavelength. This single wavelength fits around the atom's nucleus at a distance that allows the wave to interfere with itself and form a stationary or standing matter wave. In the second orbit, n equals 2, two de Broglie wavelengths fit about the nucleus, at a distance which once again produces a standing matter wave. This wave mechanical concept resulted in a new vision of the atom, which replaced Bohr's. It was Austrian physicist Erwin Schrödinger who first visualized the concept. He proposed an atom with a positively charged nucleus surrounded by a spherical cloud of electron waves. Werner Heisenberg, working with Max Born in Germany, arrived at the same model of the hydrogen atom as Schrödinger, but on the basis of different physical assumptions and using different mathematics. The wave mechanical model of the atom implies that the path taken by an electron cannot be predicted, and that the position of an electron at a particular instant can only be stated as a probability. The most dense part of the cloud is where the probability of locating an electron is greatest. We can look at this uncertainty about electron position and velocity in another way. In our macroscopic world, photons of light colliding with a relatively large mass do not measurably affect its position or rate of motion. But photons striking an object as tiny as an electron will have an effect. The means used to determine the position of the electron, light, is close to the scale of an electron. As a result, a collision between photon and electron can alter the electron's velocity. Conversely, methods of measuring electron velocity make its position uncertain. Heisenberg's uncertainty principle explains why the position and momentum of an electron in motion cannot be measured simultaneously with great precision. In other words, there is a natural limit to the accuracy of certain kinds of measurements. Mathematically, the uncertainty principle is this: the uncertainty in position times the uncertainty in momentum equals Planck's constant. As the uncertainty about one shrinks, the uncertainty about the other has to grow to keep the equation balanced. The wave mechanical model further extended the concept of the quantum. Originally, it had been used to describe bundles of radiation that could only have certain discrete permissible energy levels. Bohr extended the quantum concept to discrete permissible orbits, to which he assigned quantum numbers for reference, generally described by the letter n. The wave mechanical model defined the discrete permissible shapes of orbit clouds using a quantum number L. The orientation of that shape in space using quantum number m, and possible spins on the electron described by quantum number s. For a hydrogen atom with orbit n equals 1, there is only one possible shape. This shape has the quantum number L equal to 0. Since the shape is spherical, it can have only one orientation in space, described by the quantum number m equals 0. Hydrogen with only one electron can only ever have one spin, s equals 1/2, so we will ignore it after this example. When n equals 2, two shapes are possible. L equals 0 and L equals 1. This second shape can have several orientations in space, m equals 1, m equals 0, and m equals -1. Using this simple set of quantum numbers, an ever more complex set of energy states can be described, not only for the hydrogen atom, but at last, a method had been found for describing the more complex energy states of multi-electron atoms, and also for multi-atom compounds. This wave mechanical model has remained the accepted model of the atom since its introduction in the mid-20s. History does not record who first asked the question, how big is small? The list of those who contributed answers, however, stretches forward from its beginnings over 2,000 years ago. It is the nature of science never to close the books on any field of inquiry worthy of investigation. The next chapter of the structure of the atom is waiting to be written.